Hello, this video is Lesson 9, where we talk about analysis of variance, ANOVA. And this is part of the Applied Statistics Using Programming series brought to you from Seogang University. My name is Dr. Ian, and let's get started. In ANOVA, we are comparing multiple groups. So when we looked at one sample hypothesis testing, we were looking at testing one sample with a benchmark or a predetermined assumption about the population. In two sample hypothesis testing, we were looking at two samples and checking whether they have the same mean or a different mean. In ANOVA, we have three or more groups that we're comparing. So in the case that we have one sample and we're testing it against a benchmark, we can simply use a t-test using a one sample hypothesis test. If we have two samples that we're comparing together, we can use a t-test again. However, if we have three or more groups or three or more samples that we want to compare, then in that case we can use ANOVA. So let's talk about ANOVA. In this video, we're going to explain the concept of ANOVA. Then we'll look at one-factor ANOVA, a completely randomized model. When we use R, I'll show you very briefly a two-factor ANOVA model. And then we'll look at multiple comparison tests, specifically a post hoc test that tells us which group of our three or more groups is different from the others. So what is ANOVA? ANOVA is analysis of variance, and it's a comparison of means. Some students get a little bit confused because the name ANOVA is talking about variance, whereas we're comparing the means between groups. So don't get confused. ANOVA refers to a method for comparing multiple means of groups or categories. ANOVA allows us to compare more than two means simultaneously, so three or more. ANOVA allows one to trace sources of variation to potential explanatory factors. Those explanatory factors are the treatments or the groups, and we're testing whether there's a difference in those groups which would explain a variation in some measurement. Proper experimental design can make efficient use of limited data to draw the strongest possible inferences. So ANOVA seeks to identify sources of variation in a numerical dependent variable y. Y is sometimes called the response variable or the dependent variable, or it's just labeled as y. Variation in y about its mean is explained by one or more categorical independent variables, factors, or is unexplained. In other words, it's not related to the factors. So, variation in y, something that we're measuring, can be explained by which group that observation is from. Or it can be explained by some other factor. We call those other things as just random error. There's too many factors to contain in a model, so we can consider those as just random because they're not from our model. The variation around a mean can be explained due to factors. If it's not explained by these factors, we call it unexplained or random error. I'm going to use the most overused example in statistics, which is the average height. So in this case, let's think about our population as Seogang students. And what is the variation in Seogang students' heights? So let's say, just for simplicity, that the average height of Seogang students is 75 centimeters. Well, every person in Seogang University is not 75 centimeters, so there's some variation around that mean. Some people are taller than 75, some people are shorter than 75 centimeters. So there's variation in y, the height that we're measuring, around the mean, which is the average height. So some people are taller, some people are shorter. Some of that can be explained due to some factors. So for example, Let's say I have a factor which is which club students are participating in. So maybe there's an art club, maybe there's a history club, and there's a basketball club. And maybe everybody else who's not in these three clubs, right? So if I was using these three clubs and everybody else as my factors, well, is there any relationship between these clubs and predicting people's height? If I look at the art club or the history club, there's probably no difference between the heights of students in those clubs related to their average height. But if I'm looking at one of those clubs, which is the basketball club, it might be more likely that tall people are more interested in playing basketball, so more tall people join the basketball club. I might find that that one group explains the height of those individuals better than the average overall height. In other words, those basketball students are probably taller on average than the average Sogang height. In that case, we can explain the variation in those individuals by their treatment, by their group that they're in, the basketball group. Finally, any unexplained variation, for example, some people are still taller or shorter, and it doesn't matter which club they're in. This we can consider as random error. There's a lot of factors that affect how tall somebody is, how much they ate, what their genetics are, how tall their siblings or how tall their parents are, right? So we consider these as random error. There's too many of them to include in our model. Okay, so hopefully this gives you a little bit of a better concept of how ANOVA works. Let's look in a little bit more detail. Each possible value of a factor or combinations of factors is a treatment. So the groups. We test to see if each factor has a significant effect on Y using the hypotheses. Note that there are 4 examples right down here. So there's mu1, mu2, mu3, and mu4. In my example, I have 4 groups. You might have more or fewer groups. If we're using ANOVA, it means we have at least 3 groups or more. So if you have 3 groups or 10 or 100 groups, this null hypothesis is the same. It's saying that all the groups are equal or have the same mean. The alternative hypothesis is not all means are equal. So that doesn't tell us which group is not equal. It just tells us that at least one group is not equal. It doesn't even tell us how many of those groups are not equal. It just tells us at least one is not equal. So this test uses an F distribution, which we'll cover a little bit later in this video. If we cannot reject the null hypothesis, we conclude that the observations within each treatment have a common mean. In other words, if we have not enough evidence to show that any of the groups are different, we should assume that all the groups have the same mean. Here's a visual example of how this might work. So let's say, for example, we have a manufacturing plant that has 4 locations. One is in A city, one is in B city, one is in C city, one is in D city. And what are they measuring? In this case, they're measuring the defect rate per 1,000 computer chips manufactured. And let's say we have some observations, meaning on any given day, we counted the defect rate per 1,000 chips that were produced on that day. Okay, so if we calculate a mean, let's call it the overall mean, meaning we calculate the average of all the observations from all the manufacturing plants, we might end up with this dotted line here. This is the overall mean in this example. Let's say that we calculated a confidence interval. CI stands for confidence interval. A 95% confidence interval means we can be 95% confident that the true mean of the population of that group is somewhere in this range. We call that range a confidence interval. All right, so we're fairly confident that the mean of this D group is somewhere in this range here, which includes the overall mean of our sample. In our C group, the confidence interval here includes that overall mean. In the B group, it also barely includes that overall mean. However, in our A group, our 95% confidence interval doesn't include the overall mean of our sample. What can we learn from this? Well, that probably means if we're 95% certain that the true mean of this group is in this range up here, but the overall mean is not included, it probably means that the average of that A group is different from the other groups. Why? Because if it wasn't different, that 95% confidence interval should include that overall mean. This is the basic concept of how ANOVA is checking. So let's look in a little bit more detail. Here is another visualization of that relationship. Y, what we're measuring, is the defect rate of computer chips, and it is affected by the independent variable, the category, which location is our plant. ANOVA assumes that observations on Y are independent. Populations being sampled are normal, and populations being sampled have equal variances. This may or may not be true. However, ANOVA is somewhat robust to departures from normality and equal variance assumptions. In other words, ANOVA is still useful even if our data doesn't look exactly normal or doesn't look like it has exactly equal variances. However, it's important to understand what these assumptions mean. Let's look at the first one, for example. Observations on Y are independent. Let's say, for example, I'm measuring a stock price, and I want to measure a stock price by some treatment, maybe the day of the week, or which market it's in, or something else. If I'm looking at a stock price, the value of today's stock price is related to the value of yesterday's stock price. And the day before that, that stock price is also related to the previous day and the previous day. In other words, if we're looking at something like a time series, it's not independent because each observation is related to other observations, right? If today's stock price is, I don't know, $100, tomorrow's stock price is probably similar to that $100, either a little bit more or a little bit less, but it's related to the benchmark of where it was yesterday. In that case, it's not independent. So in that case, time series, for example, we should not use this analysis of variance model because our data would not fill the assumptions of that model. So what's the purpose of looking at these assumptions of ANOVA? Is to test whether you think your data really fits this model or not. Okay, so one way to look at this model is to say that the treatment J, meaning the group J, came from a population with a common mean, mu, plus a treatment effect, Tj, the effect of being in that group, plus a random error, E meaning error, I meaning each individual value, J meaning which group that individual value belongs to. Random error is assumed to be normally distributed with zero mean and the same variance for all treatments. In other words, if we calculate the error, we have 0 as the mean, and it follows a normal distribution around that error. The mean of each group is calculated as follows. So let's take a look at this calculation right here. What does this calculation tell us? It tells us the average of group J, that's Y bar J, the average of each group is equal to 1 over the sample size of that group, basically how many individual observations are in your group J. And then for each individual observation in group J, for all those observations in group J, add together every single value in group J. In other words, We're just taking an average of individuals in that group. That would give us y bar j. Next, the overall grand mean can be calculated as, all right, well, the overall grand mean is y bar. Y bar is just the average of our total sample. So let's look at how they calculate the average of our total sample here. As you know, from looking at basic statistics, the average is just adding up all the individual values divided by how many individual values you have. In ANOVA, we can use a different calculation to get the same result. So let's look at this equation right here. We have 1 over n. N is your total sample size. For j to c. C is the number of groups. J is each group. So in other words, for each group, add up for all the groups the next part of the equation, which is yij, meaning for each individual in group j, add them all together. Okay? Another way to calculate this would be 1 over our total sample size. So for everything in our sample, calculate the number of individuals in group j times the average of group j. And that would give you the same result. So what does this tell us? This gives us the logic of ANOVA. So let's look at the bottom equation down here. Consider that for a given observation yij, yij just means some value that we're measuring y for each individual in group j. The following relationship must hold. On the right side, we just add and subtract y bar j. So what does that mean? Let's look at this equation here. Yij, in other words, each individual who belongs to any group, doesn't matter, each individual in our data set minus y bar. In other words, the relationship between every single observation in your data set and your average of that total average is equal to the difference between the average of each group, y bar j, and the overall mean, plus each individual and the average of the group that they belong. In other words, we're splitting up the relationship between each individual and the overall mean into two parts. Those two parts are the sum of squares between treatments and the sum of squares within treatments. This gives us the sum of squares total. Let's take that example of height again. If we're looking at the difference between each individual's height and the overall average height of Sogang students, we can split that up by which group they belong to, the difference between each group and the overall mean, and the difference between the group means and each individual. So that brings us to our partitioned sum of squares. Sometimes this SSR is called SSB, meaning sum of squares between groups. In this case, I'm using SSR, meaning sum of squares regression, because regression modeling, which we'll learn in the next video, and ANOVA share a lot of similarities. So we're going to look at this again in the next video. Okay, so what this is telling us is some of the variation in what we're measuring is related to the treatments. Some of the variation is related to other factors. We can calculate this as SST, meaning the total variation in our individuals, SSR, the variation because of which group they're in, and SSE, some other reason why there's some difference. So SSR is telling us the sum of squares between the groups, and sum of squares is telling us the difference within the groups. If you think about it, if there's a large error within a group, it means some people are really tall, some people are really short in that group. It means the true mean of the population where that group came from, it's more difficult to be certain where the average is in that group because we have a really big variation. However, if we have a really small variation within the group, in other words, our error is very small, then we can be more certain, because there's not much variation in the group, that the true mean of that population is probably somewhere close to that sample mean of the group. Okay, so if we consider the degrees of freedom, we can accommodate for the sample size and how many groups we have. If we have a really big sample size, we should be a little bit more confident in our analysis. If we have a lot of groups, that means it's more difficult to compare. We need to make more comparisons, so maybe we would be less confident if we have more groups. So degrees of freedom accommodates this relationship. If we're looking at the sum of squares between groups, then we need to consider, well, how many groups are there? This gives us a calculation called MSR, the mean square regression, and the MSE, mean squared error. Okay, so SSE is divided by n minus c. N is our total sample size. C is how many groups we have. Okay, so if we combine these two, MSR over MSE, we get our F statistic. So let's look back. What does our F statistic consider? It considers how much difference we have in each group, how much difference we have between the groups. It also considers how many groups we have and how big our sample size is. So this gives us our ANOVA table. Our ANOVA table tells us our treatment, or between groups, and our error within groups calculations. First, we get SSR. This tells us if this number is very large, that means we have a big difference between groups. SSE tells us whether individuals within the groups are close to the group mean or not. If this number is very large, if SSE is very large, it means we're less confident about where the average for the true mu of that group would be. If we consider the degrees of freedom, how many groups, our sample size, then we end up with MSR, MSE. These are just the sum of squared regression and the sum of squared error after considering the sample size and how many groups we have. We put those together and we get our F statistic. Using the F statistic, we can calculate a p-value. So when we look at R, there's also a p-value next to your F statistic in an ANOVA table. Okay, so what is an F statistic? The F statistic is the most important value that we're calculating in ANOVA because it tells us whether to reject or fail to reject the null hypothesis. The ANOVA test statistic is an F test statistic, which comes from an F distribution. The F distribution describes the ratio of two variances. If we look down here, what are the two variances that we're describing? On top, we're describing the difference between groups. If the difference between groups is really large, then all groups are probably not equal. So our F value would be a very large number. If our F value is large enough, then it would be in our rejection zone, and then we would reject the null hypothesis. If there's no big difference between our groups, then our MSR on top of this equation would be very small. The numerator would be very small if there's no difference between groups, right? So if there's no difference between groups, we would have a very small F statistic. If our F statistic is small, it's closer to 0, which means it's less likely to reject the null hypothesis. Let's look at the denominator, the bottom of this equation. MSE is the error, or the within variation. So how much variation is within each group? If the variation within the groups is very large, then we're less certain. So if MSE is a really large number, what happens to F? Our F statistic becomes very small if MSE is very large. Again, that means we have less certainty about where that mean would be. So what happens? We have a very small F statistic. That means it would be more difficult to reject our null hypothesis with a small F value. Let's say our MSE is very small, meaning the variation within each group is very small. So each individual within the group represents that group mean very closely. Well, that means if there's a difference between the groups, it's not because there's a lot of difference within the groups, but it's because there's a difference between the groups. If MSE is really small, what happens to our F score? Our F statistic gets really big. If our error is very small, then if the F statistic gets big enough, we would reject the null hypothesis. Okay, so in other words, ANOVA is comparing the difference within each group and the difference between those groups and the overall mean. So let's say that our F statistic is very large and we reject the null hypothesis. If we reject the null hypothesis, what does that tell us? It tells us at least one group has a different mean than the other groups. Which group? I don't know. How much? Is it higher or lower? I don't know. How many groups? We can't answer any of these questions using ANOVA. Instead, we should use a post hoc analysis test. Post hoc means after the fact. So post hoc analysis means after we get our result from ANOVA, we want to do a follow-up test. If ANOVA is significant, we should do one more test to figure out which group or which groups is different from the others. Also, by how much? Is it positive or negative compared to the other groups? So a Tukey's HSD test will give us that information. In order to maintain the desired overall probability of type 1 error, a simultaneous confidence interval for the difference of means must be obtained. What does it mean, simultaneous confidence interval? It means we're testing all the combinations of groups at the same time. This controls for the type 1 error. The other option would be, why not just do a t-test between every group? A t-test is used to check two groups, and why wouldn't we just use a t-test to check which groups are having a significant relationship or not? The reason we can't do that is because doing multiple different tests results in an increase of type 1 error. We're not controlling for type 1 error. Instead, we should do a Tukey's HSD test, which controls for that type 1 error while doing multiple calculations at once. For C groups, so C is the number of groups, there are C times C minus 1 divided by two distinct pairs. In other words, the bigger C gets, the more groups you have significantly more combinations of groups to test. These types of comparisons are called multiple comparison tests because you're comparing multiple groups together. You're comparing all pairs of groups together. Tukey's studentized range test, or the HSD test, standing for honestly significant difference test, is a multiple comparison test that has good power and is widely used. It's named after John Wilder Tukey, who is a very, very famous statistician. Tukey's HSD test is two-tailed test for equality of pairs from C groups compared simultaneously. Why does it matter if it's two-tailed test? It just means we're checking each pair of groups and we're checking if that group has the same or different mean. It doesn't matter which direction. That's why we're using a two-tailed test. All right, so let's look at R and how we can calculate and interpret the output of these in R. Okay, so I've opened my file. First, I'm going to clear my console. So let's clear the console. And in the beginning, I'm making my data. So here's my data set. I am repeating Gyeongbokgung 3 times, so it's going to say 경복궁, 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 not easy to say. Then I'm going to repeat Changdeokgung 3 times and Deoksugung 3 times. So in other words, I'm going to have 9 values here under my tour location. Looks like this. Here are my 9 values. 1, 2, 3, 1, 2, 3, 1, 2, 3. Next, I have tour ratings. This is not real data. I just made this as an example. And our data looks like this. Again, we have 9 ratings. So what it means is our first 3 ratings are maybe tour group ratings for Gyeongbokgung. Our next 3, 1, 2, 3, are for Changdeokgung. And our last 3 are for Deoksugung. Okay, so let's put our data together into a data frame. Clear the console. Here is our data frame. All right, so we have 2 variables. One is tour location, one is tour ratings, and our location variable is related to our ratings variable. Okay, so this is how we can organize the data in order to use ANOVA. Next, I'm going to attach my data set. What does it mean to attach the data set? It means in order to use these variables from my data set, I can just use the variable name. So let's look at the average of our tour ratings. This is our overall mean. The overall mean of all of our tour ratings is 3.22. Okay? Now, let's look at just the average of each group. So let me clear this. I'm just going to run this code and then we'll describe it. Okay, so up here is my overall rating. Next, I'm looking at, in my tour data, which the tour location equals Gyeongbokgung, that's only those first 3 rows, give me my tour ratings. Again, we have, here's our data set. These are the rows that I want. I want the rows where the tour location is Gyeongbokgung, and then these are the columns that I want because it's after the comma, and I just want the tour ratings for that. If you wanted to look at that, it is just this data here. 2, 4, 3. If we look at our data, 2, 4, 3 is the values of tour ratings when we're looking at Gyeongbokgung. Make sense? Okay, so what this code here does is it tells me the average of each group. Well, the overall average is 3.2. My samples are really small, only 3 people from each group. So my question is, are these statistically significantly different or not? And if so, which groups are statistically significantly different? Okay, so we have small groups. So by just calculating the mean, it doesn't give us enough information to tell us if the difference between each group is from just randomness or because the group itself is different. So let's use ANOVA. I'm going to clear my console. It's very simple to use ANOVA, and there's actually 2 methods to get the same result. One method is to make a linear model, and this linear model is telling us the relationship between tour ratings, our y variable, and our treatment variable, tour location. How many tour locations do we have? We have 3. Okay, so in this case, I'm saying the data is from my tour data. So if you have a data set, you can indicate which data set you're using. In this case, we're comparing the vector, tour ratings, and tour location. Okay, we're making a linear model. We'll talk more about that next week in the next video. And then we're using this ANOVA function over top of that. We get the result as follows. All right, what do we have here? We have our ANOVA table. The ANOVA table in R looks a little bit different than it does in the textbook because degrees of freedom is shown first. What are the degrees of freedom? The degrees of freedom here are the number of groups minus 1. There are 3 groups. 3 minus 1 equals 2. Our degree of freedom for our SSR is 2. Residuals is the total number of values, 9, minus the total number of groups. So n minus c would be 9 minus 3, because there's 3 groups. That gives us 6. So that's how we get these degrees of freedom. The sum of squares is calculated as we showed before. Then we have our MSR and MSE. Then we have our F value. And the F value depends on our degrees of freedom. So the F value itself is probably not as useful as the P value of that F statistic. So I usually skip the F statistic and simply look at the P value. If our P value is significant at 5%, you'll see 1 star. If our P value is significant at 1%, you'll see 2 stars. If it's significant at 0.1%, you'll see 3 stars. So in this case, we are significant at the 5% level because the p-value is 0.02, which is less than 0.05. So what does that mean? That means at least one of our TOR groups is different than the others. Does it mean one is less and one is more? Which one? We need to do a post hoc analysis. Let me show you one more code. I said that both of these codes do the same thing. Let's just run the next one. AOV stands for analysis of variance, and summary will summarize that ANOVA model. And what we see is the results are exactly the same. Okay, all right. Okay, so let's use this Tukey's HSD test function that comes pre-installed in R. So I'm going to say I have this AOV model and analysis of variance model, and I'm going to use this Tukey's HSD test on my ANOVA model. That gives me this. So it's giving me the relationship between each group. So Doksugung and Changdeokgung, it's telling me that the difference is 2.6. And it's telling me that's a significant value. That's a significant difference because my p-value is less than 5%. My next relationship is Gyeongbokgung and Changdeokgung. That is not significant because my p-value is more than 5%. And again, Gyeongbokgung and Doksugung, the p-value is more than 5%. So that's also not significant. So basically it's telling me these two groups are significantly different from each other. All right. It also tells me the difference is 2.6 repeating. Okay, so I suppose this is useful, but I think there's a better function for analyzing the HSD test. So if we install the package agricole, I'm not sure if I'm saying that correctly, just choose where you are. So if you're in Korea, choose Korea here. I'm in the US currently, so I'm going to choose Pennsylvania. All right, so load your agricole package, and now we can use this function called hsd.test. And again, we're going to do the same thing. We're going to input our AOV, our analysis of variance model, which is telling you y is related to this factor, this category, from our data TOR data. And I need to input, to use this HSD test, I need to input the treatment. What is the treatment? The treatment is what is the variable of your categories, your groups. Okay, so in this case, the TOR location is considered the treatment. So I'm going to run this. It's going to save this as TOR HSD, and then we're going to print the result of our TOR HSD. So let's run this, clear the console, run. This gives us the same result in a slightly different way. Okay, so up here on top, it's giving me some statistics. I think if we jump down here, we can see Changdeokgung, Doksugung, Gyeongbokgung. These are the average of each group. This is the standard deviation of each group. And it gives us some other summary statistics for each group, the minimum and maximum values, for example, the quantiles for 25, 50, and 75. Okay, and down here, it tells us the TOR ratings and the significant groupings. What this is showing me is A is significantly different from B, but Gyeongbokgung is AB. It's not significantly different from anything in group A, and it's AB, so it's also not significantly different from anything in group B. So this, I think, is a very easy way. It will put them in order from largest to smallest, and it will give you some group IDs, which makes it easy to tell which categories are different from each other. If you have a large number of C, a large number of categories, this function is much more useful. It doesn't list every result pairwise. Instead, it summarizes the groups as shown here. Okay, so let's look quickly at two-factor analysis. Two-factor analysis means we have two factors, two treatments for each observation, two groups for each observation. So let's say I have similar data. This time I have 6 scores for each location. So let me just put my data together. Let's run this and look at what our new data set looks like. And it looks very similar to the previous data set. We have our Gyeongbokgung. This is the same data as before. But I added a new variable called sunny. So in sunny weather, these are the tour results. And in rainy weather, now I have new data for the same factors for Gyeongbokgung, Changdeokgung, and Doksugung. In other words, I have this tour location, which has 3 different groups, and now I have a weather with 2 different groups. This we can analyze using two-factor analysis. So let's look at two-factor analysis. Here is how we can write it. Here's our ANOVA function. We're making a linear model with the relationship between tour ratings, y, which is related to the location category and the weather category. Okay, so let's run this model here. All right. So what we see here is now we have 3 rows of data. The first row is the treatment groups for location. Again, there are 3 groups, so 3 minus 1, we get degrees of freedom 2. All right. Then we have our weather, our tour weather. We have 2 different groups, sunny and rainy. So 2 minus 1 is 1. That's why we get 1 degree of freedom. Here's our values. And at the end here, we get an F statistic for each one of these treatments. And we also get a p-value that's associated with that F value. So was location significant? Yes, the location is significant, but also the weather is very significant. There's a significant difference in scores when the weather is sunny or the weather is rainy. All right. But this doesn't tell us which groups are positive or negative. It doesn't tell us which groups are different. So we can, again, use that HSD test. So let's run this HSD test here. And this one shows you every relationship. So this result on top is nearly the same as before. Not exactly, because we have a little bit more information in this example. And it shows us that Doksugung and Changdeokgung are significantly different. It also tells us that sunny and rainy are significantly different as well. So let's try that agricole function and see which groups are in which categories. So here, this tells us the different groups related to both factors together. So Doksugung, when it's sunny, is positively significantly different than any groups in B. Gyeongbokgung, when it's sunny, is not significantly different from anything else. Changdeokgung, when it's sunny, is significantly lower than our Doksugung, and everything is significantly less than Doksugung when it's sunny, when it's rainy out. Okay, so these two functions are very useful. They give us slightly different information, But I find that is the most important and easiest way to interpret our results. So if you were working for this tour company, what would you recommend? I would probably recommend when it's sunny to go to Deoksugung and maybe Gyeongbokgung, but probably skip Cheongdeokgung because it is significantly lower rated than the others. However, I would also remember that I only have 3 ratings for each one of these. I think in this example, I have 6 ratings for each one. So in that case, maybe I would say you should probably get more data and then we can reanalyze this result later. All right, so this was an analysis of variance. This was lesson 9. We have one more lesson, which is talking about regression analysis. And I hope to see you in the next video. I hope this video was useful. If it was, great. I think that the R programming is much easier to see practically than trying to understand all of the equations. So actually, sometimes students get a little bit overwhelmed by all of the different equations, but when you run in R, the program, it becomes much easier to interpret the results as long as we know what to look for. If you want to be a better researcher, then I would recommend to look into the concept of ANOVA more deeply. But if you just want to use the ANOVA sometimes, then I think understanding how to use it in R is probably sufficient for you for your research. Thank you, and I hope to see you in the next video. This has been Dr. Ian from Seogang University. See you in the next video. Bye.